সেইগুলো রয়েছে, সেইখানে থেকে আলোটা আমাদের চোখে পৌঁছচ্ছে না বলে ওগুলো ডার্ক দেখাচ্ছে, অন্ধকার দেখাচ্ছে। কিন্তু এই ছায়াপথটা হচ্ছে অ্যাকচুয়ালি আমাদের নীহারিকার যে চ্যাপটা, যে প্লেটের মতন ব্যাপার, সেই প্লেটেরই তলটা আর কি, মানে ওই বরাবর যেন রয়েছে। একটু কি পরিষ্কার হলো? পুরোপুরি আমি জানি না।
No. So I have a very bad connection today, very bad. It's going in and out. But I also wanted to say that at any point, Stefan, when you need to, or Jeff, or anyone, you need to interrupt us, please stop us. We are just going on and on because we know the telescope dome is shut. But if you need to interrupt us, don't hesitate. That takes priority, of course. Stephanie, Monika, Rafael, please interrupt us. And if you want to understand something we've said in Bengali, please ask.
Yes, got it.
You do have some time because right now we're still over limits. And once it does go back into the green, it's going to be at least 20 minutes before I open the dome.
Got it.
So is this because of the wildfires in California?
No, yeah, it is because of the wildfires in California. Exactly. Now, so the main
if
session.
That is the case, I'm gonna go run and walk around and move around a bit, and I guess if we start observing again, message me on Slack. But should I give Raja or someone the screen?
Stefan.
Make Stephanie the host.
And right now we have at least 30 minutes.
I would recommend to also pass on your number or wherever we can get like hold of you immediately.
Oh yeah, we'll do, definitely. No, I'll only be gone for about 15-20 minutes at most, but
just in case.
Yeah, definitely. Hold on, let me stop sharing, and then I will put my phone number into the Slack.
Okay. And will you be able to share your screen, Stephanie?
Yes.
So Ankita, you've just joined. Can you tell us a little bit about yourself? Thank you, Stephanie. Thanks for sharing.
Okay, just 1 second, Monika.
Yeah.
So I put that transient in, like it says like NOIRLab, and it looks like really unreliable.
Yeah, it's I1C.
So I need to step away, unfortunately, just for a little bit. I'll be back.
Yeah. Stephanie, I think like something is going wrong with our extraction towards the right edge. So redwood of 7,000.
Yeah, there was like huge cosmic rays like in every frame. So I had to like blotch out like a lot of that side basically. And it was just like a bunch of noise either way.
So do you mean, so first of all, is the green one the spectrum you extracted?
Yeah.
Okay, then the flat plateau like stuff between 7,000 and 8,000, that's kind of like, it's not real, right? Because you blotched it.
It's fake. Mm-hmm.
Okay. My guess would be, so you should do a trick there, and that is, do you see the next wave on the left side where it's written 10,000? Limit that to 7,000 and see if you get a good match. Yeah, and then click fit with priors.
I feel like,
I would say like 1C.
I was thinking 6,500. Okay, yeah.
-10 to -2. And you want to, okay, you're getting a reliable match there with 1C norm. The first two is 1C norm. So all these 1Cs and 1Bs and all, if it is not a 1A, they are a bit tricky. So what you want to, I mean, definitely I could see a good match, right? Like until maybe around 5,500, right?
Yeah.
So that one, but beyond that, you can see there is a good match for the 3 big absorptions there. So do is probably kind of double check the parameters returned there. So -10 to -2 is the phase that they're expecting. So does that match with the epoch where we have taken the spectrum?
Mhm.
And redshift. Yeah, we took the spectrum today, right? So today is 18. That's like that's basically like, you know, after 50, after the last data point. Yeah. No, that
Yeah.
that doesn't matter.
But I feel like that would be the peak.
I mean, yes, the phase references with respect to the peak, and yeah, I agree with you that it's because there aren't any data points, right? There's a big gap between the first and the second. So it's possible that the peak was there, or we are still not yet at the peak, sort of close to the peak, or right at the peak itself. Who knows? So if you go back to your dash, so yeah, I'm not very, I'd say that not very comfortable with the age of the phase that returned -10 to -2. One thing you can check is if you can independently verify the redshift, and that for that, I want to see if there is a host galaxy that was visible, right? If you go back.
Mhm.
Right, so there's that nearby host, and if you can
Over here?
scroll, yeah, that particular, yeah, that blob there.
Okay.
So I guess, and the thing you want to target is if there is a redshift available for that galaxy, and if you scroll down, there are some options to do that. Okay, I don't think they have. Okay, you have to scroll up because we would match with other galaxy catalog, and we would have, you know, if it was observed before, then we should have had a redshift. So your bet is if you is something, are we on it? Okay, never mind. Click on Sinbad. And submit the query again. We're just taking a larger radius. Oh, righty. You see that galaxy, right? Like it returns within 2 arc minutes, these 2 matches. Yeah, that one. That's what we want to. There is a redshift available from some other survey. So you want to click on that. So the first one. And see if people have taken a spectrum to get the redshift of that galaxy. You will find the information at the top, and the answer is no. Nobody has taken a redshift measurement, right? Normally you'd see a Z or
Yeah.
whether there's redshift taken. This is very tricky. Yeah, I feel a bit I would say unsure about kind of classifying the 1Cs.
Mm-hmm. So maybe this is like a save for later spectrum.
That's what I would recommend. And also, let's do this. But for a time being, like just send me the text, the spectrum, the TXT file, and then proceed with the spectrum with the reduction. I mean. I guess like Stefan should have shared his screen so that you could do the reduction.
Yeah. Rafael, do you also have access to the VPNs?
Okay, I am back.
I'm testing it now, but I
Okay.
presently like now.
Okay. Do you want me to share my screen again?
Yep.
Yeah. Okay. All right. Share my screen. Okay.
Hi. So if there's no, discussion on the observation going on right now, maybe I can ask the others who are speaking in Bengali if they have any questions. তো অনিন্দ বা জয়ন্ত, তোমার যদি কোনো প্রশ্ন থাকে করতে পারো। There's someone called Abir Pradhan. Abir, are you also a Bengali speaker?
Yes, sir.
Okay. তো যদি কোনো প্রশ্ন থাকে বাংলাতেও করতে পারো।
আচ্ছা।
হ্যাঁ, এর আগে আমরা আলোচনা করছিলাম আকাশের ছায়াপথ নিয়ে, তবে এখন এই যে স্ক্রিনে যে ছবিটা রয়েছে তার মধ্যে আবছা যে একটা আড়াআড়ি ভাবে যে একটা জিনিস দেখা যাচ্ছে, সেটা হচ্ছে আমাদের আকাশগঙ্গা বা ছায়াপথ। সেটা কেন এইভাবে দেখা যাচ্ছে, সেটা মানে কি, সেই নিয়ে আমরা আলোচনা করছিলাম এর আগে। অনিন্দ, তোমরা কি কলকাতায় আছো না কলকাতার বাইরে কোথাও আছো?
ইয়েস স্যার, আই এম অনিন্দ। আমি কলকাতাতে আছি।
আচ্ছা আচ্ছা, সরি আমি তুমি বললাম, হয়তো হয়তো বয়সে তুমি
না না না, নো
হ্যাঁ,
প্রবলেম, নো প্রবলেম,
হ্যাঁ।
কোনো অসুবিধা নেই।
তো তুমি কি স্টুডেন্ট কলকাতায়?
হ্যাঁ,
আচ্ছা আচ্ছা, কি কি নিয়ে পড়াশোনা করো?
আমি জিওগ্রাফি নিয়ে কমপ্লিট করিনি, তো অনার্সটা
Okay.
আমার কমপ্লিট হয়নি, তারপরে আমি এমএসডব্লিউ করেছিলাম, তারপরে এখনো চলছে পড়াশোনা।
ওকে। আচ্ছা, এর আগে পুরোগ্রতা তখন বলতে বললেন ছায়াপথ টা কি ইত্যাদি, সেটা কি খানিকটা পরিষ্কার হলো?
হ্যাঁ হ্যাঁ,
হ্যাঁ, এটা কলকাতা বা শহরাঞ্চল থেকে এটা দেখা মুশকিল, কারণ এটা বেশ আবছা, কিন্তু গ্রামের দিকে গেলে বা অন্ধকার জায়গায় গেলে তখন দেখা যায় আকাশে।
হ্যাঁ,
এটা মানে হ্যাঁ বলো।
মানে এই ছবিটার সঙ্গে পুরোপুরি ভাবে তো সেই রকম ভাবে পরিচিত হয়নি যে এইরকম আকাশগঙ্গাটা এইরকম দেখতে, হ্যাঁ আকাশে সেটা দেখবো, মানে এটা আকাশগঙ্গা বলে সেই রকম ভাবে হয়নি।
রাইট রাইট। না এমনিতে মানে সমস্ত তারার মতনই এটাও মানে ওঠে এবং অস্ত যায়, কারণ আমাদের পৃথিবীতে ঘুরছে, কাজেই আকাশে সবকিছুই ওঠে এবং অস্ত যায়, পূব থেকে পশ্চিমে সরে সরে যায়। তো এটাও সেরকমই। এটার শুধুমাত্র যেটা বুঝতে হবে যে এটার মধ্যে অ্যাকচুয়ালি অনেক অনেক তারা রয়েছে এবং অনেক গ্যাস এবং অনেক ডাস্ট রয়েছে, এবং সেই জন্য এটা এইরকম একটা ব্যান্ডের মতন বা একটা ফিতের মতন, একটা নদীর মতন আকাশে দেখায় আর কি। তো সেইটা। আর এবং এই আকাশে আমরা যে তারাগুলো দেখি মানে প্রত্যেকটাই আমাদের সূর্যের মতন মোটামুটি ভাবে, একেবারে ঠিক আমাদের সূর্যের মতন না হলে কোনোটা সূর্যের থেকে ছোট, কোনোটা সূর্যের থেকে বড়, অনেক বেশি উজ্জ্বল, অনেক আবার ডিম বা সূর্যের যা যত বয়স তার থেকে কম বা বেশি সবই হতে পারে, কিন্তু ওভারঅল সবকটাই আমাদের সূর্যের মতন যে তারাগুলো আমরা আকাশে দেখছি।
হ্যাঁ,
Sir, how can I become an astronaut?
অ্যাস্ট্রোনট হতে গেলে প্রথমে মানে এমনি সাধারণ পড়াশোনাটা করতে হবে, এবং তারপরে অ্যাস্ট্রোনট আর অ্যাস্ট্রোনমার কিন্তু এক জিনিস নয়। হ্যাঁ, এখানে যাদের তুমি দেখছো তারা কেউই অ্যাস্ট্রোনট নন, তারা অ্যাস্ট্রোনমার, অর্থাৎ তারা অ্যাস্ট্রোনমির বা জ্যোতির্বিদ্যার নানান জিনিস নিয়ে পড়াশোনা করেন, সেই নিয়ে গবেষণা করেন। আর অ্যাস্ট্রোনট হচ্ছেন যারা রকেটে করে যাদেরকে মহাকাশে পাঠানো হয় অল্প দিনের জন্য। দুটো জিনিস এক নয়। অ্যাস্ট্রোনমাররা পৃথিবীতেই কাজ করেন, যদিও তারা পৃথিবীর টেলিস্কোপ বা মহাকাশের টেলিস্কোপ এই সমস্ত কিছু থেকে যে ডেটা বা যে তথ্য পাওয়া যায় সেই নিয়ে কাজ করেন। আর অ্যাস্ট্রোনটরা যে সবসময় শুধু অ্যাস্ট্রোনমি বা জ্যোতির্বিদ্যা নিয়েই কাজ করবেন তা নয়, তারা তাদের আরো নানান রকম তাদের টাস্ক থাকে বা অনেক কিছু নিয়ে তাদের কাজ করতে হয়, এবং সেটা অন্য, মানে আমি শুধু এটুকু বলতে চাইছি যে অ্যাস্ট্রোনমার এবং অ্যাস্ট্রোনট দুটো শব্দ শুনতে একই রকম হলেও তা নয়। হয়তো এটা জানাই আছে। তবে এই তো পুরোগ্রত এখানে এসেছেন।
আচ্ছা, এটা কি আবিরের প্রশ্ন ছিল এটা?
হ্যাঁ হ্যাঁ হ্যাঁ,
আচ্ছা,
যে অ্যাস্ট্রোনট হতে পারা যায় কিনা।
আচ্ছা, আর আবি বাংলা বোঝো তো?
হ্যাঁ।
তুমি কোত্থেকে এই যে এটা এই সেশনটা যে হবে তোমাকে কে জানালো?
মামা।
তোমার মা জানিয়েছে? আচ্ছা আচ্ছা,
বলো।
তোমার মা আছেন ওখানে?
হ্যাঁ হ্যাঁ আছেন।
আচ্ছা।
নমস্কার।
নমস্কার নমস্কার আপনি কি কোত্থেকে জানলেন এটা কি সোনালীর কাছ থেকে জানলেন
এসটি মনস্টার্স গ্রুপের ক্লাসে জয়েন করে তো
আরেকবার বলুন আমি প্রথমটা শুনতে পাইনি আরেকবার বলুন
এসটি মনস্টার্স বলে সোনালী ম্যামের
স্টেম মনস্টার্স হ্যাঁ সোনালী দত্তর
সোনালী ম্যামের কাছ থেকে জানতে পারি ওনারাই এটা লিংকটা দিয়েছেন
Anish, this is a program called STEM Monsters, started by someone who is studied at IIT. She's based in Bangalore, and she started something called STEM Monsters that just brings experiential learning to children, of young children. মানে 5 বছর থেকে 5 থেকে 14 বছর ওই রেঞ্জ একেবারে বাচ্চাদের জন্য। So fantastic. Thank you, ma'am, for connecting Avi to this session. এটা আমাদের না বারবার হবে এটা আজকে যেটা হলো এটা আমাদের এই বছরের অগস্ট মাস চলছে অগস্ট সেপ্টেম্বর অক্টোবর নভেম্বর ডিসেম্বর এই 5 মাসে আমাদের বলে এরকম 40-50টা সেশন হবে বিভিন্ন টেলিস্কোপে
আজকে আবি স্কুলে চলে গিয়েছিল তো আমি শেষটুকুনেই ওকে জয়েন করাতে পেরেছি তো আরো যদি প্রোগ্রাম হয় আমার কাছে যদি লিংক আসে তো আমি অবশ্যই চেষ্টা করব ওকে জয়েন করানো
আর আবির বোধহয় রেজিস্টার করেছে ওর ইমেল এখন আমাদের এতে আছে আমাদের দেখি আমি একবার দেখে আপনাকে বলছি
হ্যাঁ থাকা উচিত আমি গুগল ফর্ম ফিল আপ করেছিলাম
হ্যাঁ আপনি যদি ফর্ম ফিল আপ করে থাকেন আমি দেখে বলছি এক্ষুনি আবির বোধহয় নামে হ্যাঁ এই তো আপনার তো mou.ber তো হ্যাঁ আমি সেটা দেখছি এখানে হ্যাঁ হ্যাঁ আপনার নামও আমি দেখছি এখানে থ্যাংক ইউ হ্যাঁ আপনাকে ডেফিনেটলি পাঠাবো আপনার মেইলিং লিস্টে আপনার নাম ইমেল এখন আমাদের মেইলিং লিস্টে আমি পাঠিয়ে দেবো
ওকে থ্যাংক ইউ
thank you no in fact we have a few people who have joined from STEM Monsters very good.
Yeah,
and this is a brand new connection so this is a brand new connection because Shonali and I spoke for the first time yesterday. That's how new the connection
is.
Oh,
I see.
So it's very, very recent connection.
Sure.
We had connected on LinkedIn and then গতকাল প্রথম আমাদের কথা হয়.
Okay.
Acha. Sorry, I interrupted what was going on, but
no, nothing much. I mean, she was asking how one can become an astronaut.
Now, I have met some astronauts, and you can study astrophysics, but that doesn't bring you any closer to becoming an astronaut. But if most astronauts, at least Ami jotto jani, most astronauts have training in the Air Force, or they have some kind of flight training.
Right. I think
through the Asha, oneke flight training, Air Force, either commercial air or Coast Guard. At least at a US কথা বলছি that is the background of most astronauts
right কারণ একটা জিনিস হচ্ছে যে একটা শারীরিক ফিটনেসের চূড়ান্ত শারীরিক ফিটনেস দরকার হয় এবং সেটা ইনশিওর করার জন্য আমার ধারণা যে টিপিক্যালি ঘোড়ার ট্রেনিংটা হয়তো শুরুই হয় যাদের সেটা অনেকটাই রয়েছে সেই রকম দিক থেকে যার জন্য আমার ধারণা ইন্ডিয়াতেও যে কজন অ্যাস্ট্রোনট ট্রেনিং নিচ্ছেন বা আগে একজন দুজন যারা গেছেন মহাকাশে তাদের ব্যাকগ্রাউন্ড রাকেশ রাইট তাদের ব্যাকগ্রাউন্ডও এই আর্মড ফোর্সেস থেকেই হয় টিপিক্যালি আমার এই মুহূর্তে ঠিক মনে নেই তবে ডেফিনেটলি ডিফেন্সের ব্যাকগ্রাউন্ড থেকেই আসে
And Indian origin অনেক অন্য astronaut আছে Kalpana Chawla who lost her life in the Columbia accident. আমাদের চেনা একজন Sunita Williams. She's half Indian. So okay আমরা বেশ ভালো করে চিনি আমার স্ত্রী কিন্তু নাসা কাজ করে and she works with astronauts. That's how I know her. একবার শর্মিলা ওদের ট্রেন করছিল ওদের অ্যাস্ট্রোনটদের ট্রেন করছিল আর ট্রেন করছিল স্পেসে যাওয়ার আগে ওরা যে এতে স্পেস শাটল তখন স্পেস শাটল চলতো স্পেস স্টেশনে যাবে তো একদিন মিলা এরকম সুনিতাকে একটা ইমেল পাঠিয়েছে যে তোমার কি এখনো তোমার ট্রেনিংটা কি শেষ হয়েছে হ্যাভ ইউ বিন এবল টু টেক ইউর শাটল ফ্লাইট এরকম ইমেল পাঠিয়েছে কোনো উত্তর নেই 1 সপ্তাহ 2 সপ্তাহ কোনো উত্তর নেই which is very unusual of her And then এরকম 2 সপ্তাহ পরে একটা ইমেল এসছে ওর কাছ থেকে to Mila, and she immediately forwarded to me. She said, "I'm sorry for my slow response. I'm writing from the International Space Station."
Right. Yeah.
Acha.
Okay, I think now we have people.
Yeah, we have the main
counting
session
on the
starting.
speaker.
We have the main
Yeah.
session starting. Of course, you don't need to leave. Anyone who's already part here is welcome to stay on. You don't have to. And I will just announce to the crowd in a few minutes, since it's 3 minutes before the start of the session. I'll wait for it to start. And once it starts, I'll announce to the group that, what the situation is with the telescope. Anish, you've done a tremendous experiment today. Khub bhalo. I've
No,
been enjoying your explanations.
No, but yeah, I don't know. I mean, this is the first time that I'm doing this, so not at all. But
yeah.
this is how I
You're a
at least
pro.
thought of it when I first thought of the Milky Way. So I thought that it's just
Wonderful.
like
Wonderful. Really, really very good.
And so what things are present in space shuttle?
Sorry,
Hari?
Abhi, say that again.
What things are present in space shuttle?
What things are present in the space shuttle? Of course, people, equipment, food. There is often scientific experiments are carried out in the space shuttle. We had written a proposal to NASA to build a telescope to be carried by the space shuttle. So many things like that.
I have a question.
Yes, please.
What is the name of the space? Like, there were people in the spaceship that went to Saturn but landed on Titan. It went to Saturn, observed. Were there people on the Cassini?
No, there were no people on Cassini that landed on Titan. That's a very good question. No people have landed on anything other than the moon. There hasn't been any Mars landing. That's the next frontier. There have been unmanned missions that have landed on various things, as you said, like the Cassini mission, but there's been no humans sent to anything. No humans have landed on anything beyond the moon.
I have another question. The
Yes,
spacecraft Galileo, it went in
Yes.
Jupiter's atmosphere and crashed apart, right? Or did it?
Yeah. I don't remember now. Anish, do you remember? Is it spacecraft Galileo? There was a spacecraft called Juno that was inserted into Jupiter, that actually crashed into Jupiter by design. But I don't.
Right.
Was it Galileo? I don't remember what the Galileo mission was. I don't track all these
Galileo
missions
was
very well.
like a machine, and then there was the three Lego people. One of that Galileo Galilei, and then the Jupiter god and the Greek god Zeus, and then his wife Juno.
Yeah.
right.
That
Very
was
good.
spacecraft.
Very good.
But how many minutes it takes to
So I'm going to
reach
make
the
a quick
space?
announcement. Yeah, sorry. Go ahead. Go ahead.
No. I was just going to ask the kid that do you know the connection of Galileo to Jupiter? What's the connection between Galileo and Jupiter?
That's right. You mean the human being Galileo with
The human
planet
being
Jupiter,
Galileo with the planet
with
Jupiter.
the planet Jupiter.
Excuse me, sir.
But let's
Excuse me?
answer the question first before we ask another.
Sir, so how many minutes it takes to reach the space?
Galileo and yeah, go ahead. What is the connection? Did you want to answer the question, Abhi?
Sir, I have another question.
No, but we want the answer to the first
I
question.
think
Then
the answer is that Galileo Galilei discovered Jupiter's 4 biggest moons: Callisto,
very good.
Io, and then Ganymede and
Ganymede.
Europa.
Great.
Very, very good.
Very good.
Very good.
And why was
very
it
good.
so
That's-
important? Why was it so significant, this discovery? Why is it considered so important?
I will give you a
I
hint.
think
Galileo
it's-
nearly
I'm
died
not sure
because of
this
it.
one, but I
Yeah.
think it's because 3 of the moons of Jupiter, the 3 biggest moons, scientists think there's a teeny weeny chance of life.
No,
Not-
that's
not why.
that came
That's
much
not why.
later about Europa.
Yeah.
Yeah,
But I think Galileo showed that the Earth is not the center of the solar system.
Right. So this was the first instance where, so because Galileo inferred or concluded that these are moons of Jupiter, so they are going around Jupiter. So this was the first instance where something appeared to be moving around something other than the Earth. Because if you look at the sky every day, you think that everything is going around the Earth, right? Because everything rises in the east and sets in the west. But this was the first instance where Galileo showed that not everything in the sky is going around the Earth. These moons are going around Jupiter. So Earth's special position as the center of something around which everything revolves was taken away. Earth was sort of dethroned. So
was demoted greatly. And the church took such offense at this that Galileo nearly lost his life. He was nearly killed.
Right.
Isn't that right? He was.
Yeah, of course. yeah.
And there were others who followed with this, like Copernicus. It's often also referred to the Copernican revolution, that things go around the sun, not around the Earth. So let me, Abir, you had a question. Please ask that, and then I want to make a quick announcement after that. Go ahead, Abir.
Sir, how many minutes it takes to reach in space?
How many minutes?
It takes to reach in space.
Didn't understand.
Sir, how many minutes it takes to reach in space?
In reach.
To reach in space. By what? You mean a spacecraft to reach space, or for how long does it take for a rocket to reach space?
By rocket or space shuttle?
It depends on your definition of space, of course, right? Right, Anish, am I missing something, right? Because it takes a fraction of a second to leave to go from being on the Earth to leaving the Earth's surface. That takes, literally a matter of a second.
Yeah, but I think basically if you define,
going into orbit,
you're right.
Yeah, going into orbit though takes hours, a few hours.
Right.
I have another question. How long was
sure.
Yuri Gagarin in space?
I don't remember how long Yuri Gagarin was in space. He was the first human to go into space, and it was around the time I was born.
Minutes? I think 108 minutes, but I'm not
108
sure.
minutes, okay.
I don't think so, but I'm not sure.
It was in 1962, I think. It was the year after. It was a few months. Within a few months of my being born, Yuri Gagarin became the first human to go into space. All right. So for the group that's gathered here, there's 19 participants here, many of whom are 19 people on the Zoom call. I see that that includes, of course, the science team. That's 1, 2, 3, several people on the science team. 3, 4, 5, 6, 7 people. 6 people on the science team, and at this point, 13 participants. I have to give you the bad news that the telescope is closed because of the California wildfires. It was open earlier, but the smoke in the air got worse. And to protect the telescope, they had to shut the dome of the telescope. So the telescope currently isn't collecting data. But we are, of course, we decided to go ahead with the Shadow of the Scientist session. And it's a small enough group that we're happy to entertain questions from those of you who are here. They could be about the telescope and experiment we're doing. But let's go around and make sure everyone has a chance to ask a question, right? Because some people have already asked questions. Let's see if there are questions from others. So if you already asked a question, please wait till you see if others have any questions before you ask your next one, okay? So there are many people question doing what experiment we're doing tonight, well, would be doing tonight if the telescope were not shut down by smoke. And feel free to type it into the chat, or you could speak up. It's a small enough group. You can just unmute yourself and speak. Why don't we at least go around and tell us where you're connected from? You know, start. I can call out names, but if you wouldn't, why don't you do this yourself? So Ayush Dugar, if you tell us where you're from and how you found out the sign. We then go to Aparajita. Okay, so how about you, Ayush? Where are you connected from? Yeah, go ahead, Aparajita. You can unmute.
Yes.
Yeah.
Yes, sir. I'm from Kolkata, India, and I actually got to know about this meeting or event from our astronomy club in our school. Our astronomy club is called Skylab, and I've been a part of it for 2 years now. So our advisor recommended us joining this meeting and getting to know a bit more about space. And she said it would be a lovely opportunity for us to connect and ask questions. So that's where, that's how
wonderful. Are you at La Martiniere Girls, or?
I'm sorry?
Are you at La Martiniere? Which school are
No,
you?
I'm from Modern High.
Modern High School. Okay.
for girls.
Okay. Yeah. Okay. Yeah. I was at your school, right, last week, presenting this. I don't know if you were there, but there was a class 9 and class 11 were in the session that I did a session at Modern High School last Thursday, last week.
Oh, I was not there. Our club actually happens on Tuesdays every week.
I see. Okay, no problem. Thank you for joining. And in fact, what I'm going to do is, Stephanie, you're sharing your screen. If I can take the screen share from you and share my screen, that would be amazing. Thank you. I'm looking for a particular thing that I was going to share. Here we go. Anyone else wish to introduce yourself? That was a very nice introduction. Thank you so much.
I am from Chennai. And
Yes.
I got to learn this from my science class, STEM Monsters.
Fantastic. Thank you, Shankar. Thank you for joining. So I'm going to share my screen and show you an image of the sky that was taken with not the telescope we are using tonight, but a different telescope. And this is an image that is, it's an image of galaxies in the constellation of Virgo. And you should see the detailed image appearing gradually, because there's so many pixels that it's hard for it to display it at full resolution. So it takes a little while. I want to show you a beautiful galaxy that is really like a train wreck. It's crashing into a galaxy. So that you're a STEM monster connection. Anyone else wish to introduce themselves? So if you were here earlier, you heard about the Milky Way, which the Bengali word for that is Akash Ganga. This is an example of a different galaxy, not the Milky Way, that we are seeing from the outside. And this is located about 50 million light years away. These two galaxies that you see are located about 50 million light years away.
Are they located 50 million light years away from us?
From us, exactly. Not from each other. They're much closer to each other than that. They're about, in fact, they're about a million light years away from each other, of that order.
A million light years?
Yeah, but they're 50 million light years away from us. Each of these two galaxies.
I thought they were a bit closer. 50
So our distance to the nearest big galaxy for us, the Andromeda galaxy, is 2.5 million light years away. So that's why I say 1 million light years away is not a very big separation. That's a typical separation between galaxies.
Excuse me, sir.
Yes.
Sir, does our galaxy also revolve?
Does our galaxy also revolve or rotate? Yes, it does. It does.
Wait, what does it rotate around? I know the sun rotates around the universe, but I don't know that it rotates around the galaxy. But what does
So
the
the
galaxy rotate around?
The sun doesn't rotate around the universe. I
I
should
mean, not
stop
the
you there.
universe, I mean galaxy. I mean galaxy.
So galaxy, okay, so the sun goes around the center of the Milky Way galaxy. Our galaxy is in an orbit with Andromeda. They are actually in a plunging orbit with Andromeda. It's falling towards Andromeda.
Yep.
Anyone else want to, Aparajita, you've already introduced yourself. I'm going to call on Avisha, if you wouldn't mind introducing yourself, and then Hamad.
Can I introduce myself?
Yeah, please go ahead, Avisha. Tell us about yourself.
I'm from India, except I live in Singapore, and I got to know about this session from my STEM Monsters teacher.
Fantastic, fantastic. So you're based in Singapore, is it?
Yeah.
Okay, wonderful. I'm actually going to be traveling through Singapore on my way from Kolkata to California. Wonderful. And let's see, Hamad, are you able to introduce yourself, please? Did you find out about us? Muted, but can't hear you. Try one more time, please. There's something with the audio that's not coming through. You could also type into the chat.
Raj, I think you might be having connection problems. It sounds like you've been cutting in and out for the last 30 seconds.
Yeah, you could also type. You could type into the chat if you prefer, Hamad. How about Aryan Kejriwal? Would you like to say a little bit about yourself? You know, the reason we're not doing our science experiment is because the telescope is closed due to smoke. And I have a picture of galaxies in the Virgo cluster on the screen as entertainment. I just zoomed out to show you a few more galaxies. And now I'm panning across. This galaxy that my cursor is on is one of the bigger galaxies in the Virgo cluster. As we zoom out, you can see more.
So is our galaxy going towards Andromeda galaxy, or is Andromeda coming towards us?
Yes to both of those questions.
Okay.
It's both. A good way to think of it is when you have two objects, you can think of something called their center of mass, and both galaxies are moving towards our common center of mass. Of course, the position of our common center of mass changes as we move, but yeah, they're moving towards each other.
Collide at some point?
Yes, they will collide about 4 or 5 billion years from now.
How long will it take for the two galaxies to merge?
You know, that's a very good question. Big galaxies take a few billion years to merge. They take, 4 or 5 billion years to merge. So it's not an instantaneous process. But do you know how long the sun will take to complete one circle around the center of the Milky Way, roughly? Anyone know the answer to that? How long does it take the sun to go about 200 million years, about a fifth of a billion years is what it takes.
But I know that it'll take 5 billion years for the sun to
become a red giant.
5 billion years for it to die.
Yeah. So then you can do the calculation of how many times the sun would have gone around the Milky Way between now and when it dies. Now, when it dies, it won't exactly die. It will become bigger first, then it'll become smaller, it'll become fainter, but it'll still keep orbiting the Milky Way. But between now and then, 5 billion years, since it goes around the Milky Way 5 times every billion years, it'll undergo 25 of these trips before it becomes a red.
Before it becomes a white dwarf.
Right.
But we'd have probably been extinct by then.
Yes,
Roger?
if our politicians have their way, we'll be done. Yes, go ahead, please. Sorry. Yeah.
I just have to ask Monica something really quickly.
Yeah, please
And
go
then I
ahead.
also
Sorry,
have to share my
Stefan.
screen.
Of course, please, and not stop sharing my screen. Yeah. Go ahead, Stephanie.
So Monica. So for the third transient that we did, there's like two
Emission
traces,
lines.
and this is the real one, like the one above 150, and the one below it has like these features that are like seeping into it.
So those are H alpha, N2, and sulfur 2. I can see a pattern. Can you go to the 2D spectrum one more time, please, and just zoom in a little bit? Look, there's H alpha, N2, sulfur 2 associated with both targets, the lower one and the upper one. Can you see that?
These three?
Yep, exactly.
Okay. And what about these two?
Those are sulfur 2 lines. So the brightest line is H alpha. So that's Balmer emission from the electron dropping from level 3 to level 2. That's the brightest line there. And to the left and right of that are nitrogen 2 emission lines, forbidden lines. And then those two on the far right are sulfur 2. Now, the reason they're curved like that in the lower one, the reason they have that funny sort of crescent-shaped pattern is because you're probably looking at some kind of galaxy that is moving, that's rotating. And so different parts of the galaxy have Doppler shifted by different amounts. So if you have a spinning frisbee moving away from you, different parts of the frisbee are moving away from you at different speeds, and that's what you're seeing.
Okay. So I should keep these in the spectrum?
So
Yeah, but Stephanie,
you 1D spectrum. Yeah, sorry.
Wanna show Raja and us the cutout from the link from Antares, for instance, so that we know like what exactly we're looking at.
One thing I'm seeing in the 1D spectrum is the sky subtraction was affected by these emission lines. That's why you see over subtraction and under subtraction of the emission line. That's one thing I noticed in the 1D spectrum very quickly.
And what about these lines look real, right? Like they're on the blue side.
Let me see. Yeah. So the 5170 line is magnesium B. Let's see, what is the, so you see 5170 there, the one that your cursor's on now, that's that's the magnesium triplet blended together. I don't know what's at 5200 or at 5000. Let's see, what else can we see here? I'd have to look at the 2D spectrum to see. Yeah, actually, can you scroll to the right and let's see the H alpha region? A little further. Yeah, there you go. So you see what I mean? There are these dips and spikes, and the dips are because of something in the sky subtraction, nothing else. So I think that's something that's worth fixing before we can.
What is this? I'm a bit confused.
Oh, this is a spectrum. What you're seeing on the x-axis is the wavelength of light, and the y-axis is how much energy is coming at that wavelength, is being emitted at that wavelength. But this looks like just from the basis of the, H alpha in this is showing up at 6750, which is not the rest wavelength. That means it's a finite redshift galaxy.
So it starts at 0.5, right? Or like somewhere between 0.5. Start somewhere close to 0.5.
I'm not sure where you're seeing the 0.5, sorry. But okay, Stephanie and Monika, this is a galaxy. And this, I don't know why it showed up in the transient list. So.
I think, Stephanie, if you showed the cutout, like just go to the Antares link and then we'll see what's happening. Yeah, so Raja,
there you go. There's a galaxy there, right there.
The transients happening on top of as in like it's embedded in that part of the galaxy.
I wonder if is it a supernova in the galaxy?
I think it's likely. Can you scroll up, Stephanie, to see the light curve? We might have to, so it's pretty. just rising. So I'm kind of
I wonder if it's an AGN.
Oh no, it cannot be an AGN.
Okay.
Just that like we're not seeing any. It should be a very
Yeah. So if you go back to the image for a second, if you scroll down, so that's the before and after image and the difference, is it?
Yeah, that's correct.
So there's a point source which seems to be coincident with the. It's not at the center of the galaxy, because you can, in other words, the galaxy is not at the center of the cutout. The point source is. The galaxy is not centered on the cutout. So it's an off-center point source. Right? Does that make
Yes.
sense?
Yeah,
It's an off-center point source of some sort. And I don't think there's any chance that it's unassociated with the galaxy, because it is got the exact same redshift as the galaxy. Right?
So
Yeah.
if you go to the 1D spectrum, Stephanie, one thing that's puzzling is just can you zoom out? There is a big this dip there. That's yeah, I just don't think that's real. Like what's happening with I'm talking about this region between like 5,000 to 8,000, like what that big dip there.
In fact, the shape of this overall spectrum looks very strange to me. I don't know what's going on with it.
Yeah.
Is this the extraction of both traces or only one of the two?
This is both traces.
Combined, is it? The sum of the two traces.
Oh, you have to subtract it, Stephanie. Otherwise, like this is like an sort of like the example case that was included in the reduction tutorial PDF, right? Like I believe you already can see in your 2D image, the 2D spectrum, that there is a trace for the galaxy, right? So you might have to fit some sort of your background when you do your aperture selection for removing the background, you might have to fit a linear function, like something that's not linear, I'm sorry, I guess quadratic, something that's not flat.
So let me see. This is so what you can clearly see are two continua, right? So one must be the center of the galaxy, the other one must be the transient. It's a transient, not a variable, right? This one?
Yeah, that's correct.
Wow, it's very cool. Whatever this is, it's very cool.
What is this? What is this?
This is what's called a 2D spectrum, where you take the light that came through a slit and you spread it out into its constituent colors.
This file, object value, SK5, physical image, frame 2. I don't understand that.
Yeah, don't worry about that. This is something, it's a piece of software that's used to display images. It's something called DS9. You'll see that in the top of the image. It's called DS9. So I'm intrigued by the fact that the emission lines are spatially compact and associated with the upper continuum, right? You see H alpha N2 sulfur 2. All three of them, you see that little knot there. Yeah. I don't think that's a coincidence, that the brightening of the H alpha right at that location is too much to be a coincidence. It must be associated with that object.
So you guys are saying how I should fix this dip is by doing like a non-linear like background fit?
When you're doing your aperture selection in the reduction, right? I imagine that you would be seeing two bumps, right? Like one's coming from the trace of the transient, the supernova, and the other from the galaxy, right?
Yeah.
What you want to do is, I mean, it's going to be pretty blended, that once the transient light will be contaminated by the host background that you choose to fit, it cannot be flat, because the default one is a flat function, right? So if you probably like very quickly, you just open up the PDF, right, for the Kast reduction, you'd see like how they fit that line.
I mean, the shape of the spectrum is so bizarre that if it were like that, we should see that in the 2D spectrum. We should see it brighten tremendously in the 2D spectrum in the red. Do we see that? Or is it an artifact of some kind of flux calibration problem?
No, I
Anyway,
don't.
I'll let you guys get back to it.
Yeah, the flux standard, it was applied in other, seems to be working fine. Yeah, Stephanie, just right there. Can you scroll up? Yeah, that's the example I'm talking about. Do you see the way that they use an order to and then they put it like that? But what I imagine is going to happen in your case is, if you imagine that bump that you see there is a transient, then the thing that's next to it, you'd see a more elevated signal in your trace,
Yeah.
right?
Like
But
more
that
up, yeah.
exactly. But then still, like in the middle, the right side of your transient is going to be contaminated by the light from that post, right? So have to flow with it a little bit and then fit that line that has more contribution to the right side. So something that's tilted like that.
I don't understand what this is as well.
We can't explain just right now, Shankar, sorry. Hang on a minute. So one thing I was going to say, Monika and Stephanie, is the complicated shape of the galaxy's emission lines in the 2D spectrum is going to make this complicated.
Yeah.
Okay.
So if we go back to that 2D spectrum for a minute, I think the simplest thing one can do is completely mask out the central few rows, anything that involves the galaxy or the transient. And the rest of it should give you a beautiful air glow spectrum of the atmosphere. So the atmospheric air glow subtraction part should go relatively easily. That wouldn't be a problem. But we want to make sure that the sky that you're subtracting is not in any way contaminated by this funky crescent-shaped emission lines associated with the main galaxy. That's the key thing here in order to get a good spectrum. But if you scroll to the right, do you see this dramatic brightening? That's, if you just pan to the right, sorry. Yeah, see, there's no dramatic brightening. In fact, there's a sharp dip in the fluxes. Do you see that? That's the 7600 angstrom atmospheric A band. We should see that in the 1D spectrum, or has that been removed?
I did not remove that.
Well, I mean, as part of flux calibration, it gets removed, right?
Oh, okay. I thought you were talking about like this thing for a second.
Yeah, no, that's right. It tries to remove it. It's noisy over there. That's what you're seeing there. But I don't understand the shape of the spectrum, like Monika said. I don't understand why it's so extreme.
Yeah.
Okay. Now, can we explain to Shankar what we're doing here? Stephanie, do you want to take a stab at it?
Please,
So,
sir, please also explain me too.
Yeah, we're going to explain to everyone.
Okay, so basically, we get this image from the telescope and it has a trace, and this trace is our actual target. And this one has two because this is the host galaxy because they're really close to each other.
So Stephanie, I'm going to ask you to back up for a second. I don't think people know what the axes are that they're looking at. What is the x-axis? What is the y-axis? You would explain that.
Okay, so this is the y-axis, and then this is the x-axis.
No, other way around. So no,
I
that's
thought
not
it was
what
the
I meant.
other way around.
No, that's not what I meant, Stephanie. That's what I meant by what is the x and y-axis. What I meant was, I know you've rotated it. What I meant was what runs along the x-axis, what runs along the y-axis. So in this instance, when you display it like this, what changes along the y-axis is the wavelength of light. Okay, so you've got redder light landing at the top and bluer light landing at the bottom. Isn't that right? Or is it the other way around? Yeah.
So this is like the wavelength spectrum.
That's the wavelength direction. And then in this display, the horizontal direction is where you are along the slit that's used to take the spectrum.
The slit of the telescope, yeah.
So keep going. Sorry, I didn't mean to cut you off.
Yeah, so this is like the sky basically, and like this trace is our actual star. And then I take a spectrum along this trace. So I basically just subtract out these two parts. So I just have the trace. and then I can convert that into the spectrum that's here. And then these dips mean elements in the star. So that's how we can know what the star is made out of and how we can classify it too. Do you think there's anything more I need to add, Raja?
Yeah, no. So that's very good, Stephanie. Thank you. Thank you very much. You know, the thing is, we've been taking, so if I could just back up for a minute, you know, when you take a picture of something, you know, you can take pictures with your cell phone, you can take pictures with a telescope, which is what we're doing here. You take a picture of something, you see what it looks like, right? It looks, you know, it looks like a circle, or it looks like an ellipse, looks like a line. You can, you know, that tells you something about the object, but you don't learn as much as when you take that light and you break it up into the colors of the rainbow. And in an astronomer's rainbow, there are many more than 7 colors. There are thousands of colors that you can split it into. In fact, we are splitting it into, how many pixels are there on the blue side and the red side of the spectrum, Stephanie? Roughly.
I think I actually don't know that.
I think it's, is it 2000 pixels on the red
okay,
detector?
2048 pixels.
2048 pixels on the blue detector and on the red detector. So that's, we are basically taking white light and we're dividing it into 4,000 colors. 4,000 colors. And it actually, we even go a little bit beyond what the eye can see on the beyond the violet into the ultraviolet a little bit, right? Because we go down to you know, what the shortest wavelength the eye can see is about 3,600 angstroms, and I think we go down to 3,200. On the red side, on the other side, we go to about what the eye can see, as far red as the eye can see. But when you take a spectrum of an object, you understand how much energy is in each color of light, you'd really learn a lot about the physics of the object. You know, what kind of object it is, what its temperature is, sometimes its chemical composition, its Doppler shift, how fast it's moving, things like that. So spectroscopy is very useful in astronomy. That's what we're doing tonight, or we were doing tonight before the smoke shut down the telescope. So if you're just joining, smoke from the California wildfires have shut down the telescope tonight, and this is something that ground-based astronomers have to live with, interruptions due to weather or other hazards. So that's what's going on. So we were looking at some of the spectra collected earlier tonight.
Excuse me, sir.
Yeah.
Sir, what is spectrum?
Spectrum is a fancy word for what happens when you see a rainbow. That is, the light of the sun is being divided into the colors that make up white light, and that's called spectrum.
Okay, sir. Okay, sir.
You guys, I'm going to probably suggest we close the STS session today, just because, you know, we couldn't, you know, we can't do on-sky observations, but we've had excellent questions. And if there are others who want to type into the chat what, you know, where they're from and where they're connecting from, we would love to know that.
Sir, there are many sessions like this.
There will be many sessions. That is, the next one is on the 29th, on the morning of the 29th in India. It'll be the night of the 28th in California. So 20th of August. We'll have something like 15 sessions in September and maybe 20 in September, and then 10 to 15 in October, November, and December. Many sessions coming up. And then again next year as well.
Okay.
Meshika, you've been here patiently. How have you enjoyed what you've come across today? And let's see, there are others who I haven't heard from. Ahmad, Sokeen, Rob, Avisha, Ranjana. Aparajito, hi. Aparajito, I have a lot of stuff for you.
Oh, yeah.
I
joined
have a lot of
late.
stuff for you.
Yeah.
No, I have a lot of stuff for you because I had a couple of conversations that are very relevant to the work you're doing. So I have a lot of clarity on how you can move forward with those things. So,
Great.
um,
Yeah, so is the weather bad today?
it's not weather, it's particles in the air from smoke from California
Oh.
wildfires,
Oh,
that's causing us to be shut down today. But we've been looking at spectra, we've been looking at some images, and there have been some very good questions about what we're doing and what we're seeing.
The two galaxies look very close, but they're like 1 million light years
Apart,
1 million
yeah, that
light
was a
years
great example.
apart.
And there are good questions being asked on the chat. If people want to jump in and answer questions on the chat, that would be great. But I'm thinking that I will stop the recording soon of this session, just because it is, it's been one of these things where the weather is unpredictable and you run into issues with it.
Yeah, Raja, before we close, I was just going to suggest that maybe you can share your picture of the Virgo cluster again and just talk a little bit about, because one can see spirals and ellipticals there, because we were earlier talking of the shapes of galaxies.
Yes, beautiful. This one right here. So this is a great example of spiral galaxy seen on its edge. Spiral galaxy being distorted, and these two are elliptical galaxies right here. So is this one right here. I'll zoom in a bit more. Is this the image you meant, Amish?
Yeah. Just there's one particular, not fully edge on, but nearly edge on to the left of the, slightly more to the left, and that.
There's some beautiful spirals like this one over here.
Right.
This one over here.
Right. So just to point out that our Milky Way is very much like one of these.
Very much like one of those. These, in fact, the bigger galaxies in this picture are significantly more massive and luminous than our Milky Way.
And older, perhaps.
I have another question.
Yeah.
Do galaxies show bright light, or do they look like dark? Like black holes are bright, but are galaxies also like bright?
Yeah, they're bright because of the many stars they contain.
Okay.
I have a question too, actually.
Yes, please.
Yeah, so will it be safe for the people living around the time when our two galaxies merge?
Yes, it will. When galaxies merge, stars don't smash into each other. They don't, and in fact, planets are not ripped away from their parent stars. So galaxy mergers are relatively non-violent things, and it changes our view of the solar system, of our Milky Way. When the Milky Way and Andromeda galaxy collide, we won't see a beautiful line, what Anish was calling Akash Ganga in Bangla. We won't see that anymore. It'll be a blob. We won't call it the Milky Way. We'll call our galaxy the Milky Blob.
Okay. Thank you.
Thanks. That's exactly right, Stefan. The microwave background was indeed mapped from space and from balloon experiments. Yeah, we will probably be extinct by the time. I don't know about extinct, but there are many other things that are threatening us, right? Disease.
I saw in a video that an asteroid would probably collide in the Earth before these two galaxies collide.
We have ways of deflecting asteroids, so that may not be what kills us. Hopefully not. The sun will blow up. That will certainly be catastrophic for the Earth.
But I thought that's after the galaxies collide, right?
That's before. The sun will merge. The sun will become a red giant in 4 or 5 billion years from now, and the galaxies don't really start merging till maybe 5 or 7 billion years from now. So, there are more immediate things like disease. Hungry politicians, like what's going on in the Ukraine right now. There's many other dangers. I think we human beings
global warming.
What is
climate
that, sorry?
change. And climate change.
Climate change, of course, global warming, yeah. We human beings are a bigger danger to ourselves than anything else.
Yeah.
In the immediate term, in the short term.
I have another question actually.
Yes, please.
Since the galaxies are so far away from us, do we know if they still exist?
That's a great question. We think they do exist still because galaxies have lives that are billions of years, many billions of years. And the galaxies we're looking at here are only 50 million light years away. So I think natural inference would be nothing has changed drastically for them, because galaxies, when I say life of a galaxy, our Milky Way's appearance will change a little bit over time as stars age out and die and new stars are born. But it doesn't change that drastically over periods of billions of years. And the galaxies you're looking at in the screen are only 50 million light years away. I say only because that's 1/20th of a billion years. And does that make sense?
Yeah.
It's a great question, Token. Sorry about all the
Milk
background noise.
Andromeda was what I created for the Milky Way and Andromeda colliding appear. I
Very
just
good.
created that name.
Milkromeda.
Yeah, Milkromeda.
What
Milky
other
Way plus
astronomers have been
Andromeda.
calling it, I'll put the name in the chat. What other astronomers have been calling it is Milkomeda. It's spelled like that.
Oh, so close, right?
Very close. But these are not official names.
Milkomeda.
Raja, just really quickly, if I can share my screen.
Yeah, sorry about that.
I have another question. What if all the stars that can do supernova did supernova in the universe? Like, what if all the stars did a supernova in the universe? Like all the stars except the stars that cannot.
Shankar, just wait a moment, please, because we want to look at this together. Stephanie, what are we looking at?
So these are the traces. This is the transient trace, and this is the galaxy trace. So is this what you guys meant by?
Yeah.
Okay, so I did this before, so I feel like I'm gonna get like the same result.
So it's not doing this is why it's over subtracting. You can see that the dashed line, instead of being a baseline, is let's see. I think the dashed line should be steeper and it should connect. I don't know. Can I steal your cursor for a moment? I want to request remote control. Okay, I would have it start there. Can you see my cursor?
No, I can't see it.
Okay, so it would start at, let me just say it, from about -8 in X, column number -8. And yeah, that level, even lower down, little bit to the left and down. If you drew a dashed line a little further to the right, yeah, and up to the level of the flux, of course. Yeah, from there, if you were to draw a curved line that connects to the point at column number, say 3, and flux level of 2700. To the dip, little lower, to that dip. Basically, here's the thing you're trying to if the transient had not been there, what would the rest of the spectrum be doing? That's what sky subtraction is. That is, what would we have seen if the transient had not been there? That's the definition of background subtraction or sky subtraction. So if you imagine the transient to be a sort of a roughly Gaussian shaped thing, what is it sitting on? That's the thing we're trying to
I don't understand what you're saying.
That's okay. I'm using big words like Gaussians. No worries. You'll study about them. So that's, and Monika, I see what you mean about fitting a curved baseline, because the galaxy's light is falling off, not in a straight line in these coordinates. It's more like a curve.
Yeah. And one thing
Raja, just to interrupt.
Yeah.
Sorry. I mean, this is just a thought. So if you were saying that the transient should just add on to the background of whatever is there, the galaxy or something, then shouldn't that curve be a little lower than that dip? Because at that point, the transient still has some flux, right?
Exactly.
I
So
mean,
what people sometimes do is you take the main galaxy, and if you draw a vertical line a little bit to the right of where your cursor is, Stephanie, if you draw a vertical line at, let's say, the at x if you draw a vertical line there, and if you were to do a reflection, if you reflect the right side of the galaxy and subtract that off, that would be a beautiful way to do this. Now,
exactly,
it would not account
Where's
for
the
the
galaxy? You said right side of the galaxy, but where's the galaxy?
The galaxy is the taller peak.
Galaxy is the what?
The taller of the two peaks.
Oh, the tallest one that looks like the mountain?
Yes. Yeah. So Stephanie, that would be an empirical way to do it, is take the thing on the right, reflect it, subtract it from the, and I don't know how you would do that, but it would not account for the emission lines because they have complicated structure to them.
Excuse me, sir.
Yeah.
Sir, what is this called?
I'm sorry, we can't explain that. That's too general a question. I'm sorry. Are you trying to define a baseline, Stephanie?
Yeah.
Okay.
Do you think like this is like kind of good?
No, go further to the right. Go further to the right. Further to the right. No, even further to the right. Somewhere there. And then at something like 100 and so you're
more to the left, or
no, sorry, you're going to give it two markers, right? One to the left, one to the right, and you're going to connect those two. Is that what you're trying to do?
Yeah. Just yeah.
So the ideal way to fit something like this is to say, I'm going to fit a polynomial to this range of pixels and that range of pixels, and ignore the part in the middle where the transient is.
What's a polynomial again?
I'm sorry, I don't know. I can't explain to you right now. Okay, so I think, what you have to do for something like this is you have to mask out a region and fit to the wings. Shankar, Shankar, I want to say that you have not read our code of conduct when you join this, right? Because you're supposed to let the experiment go forward. That's paramount importance. This is not a class, right? It's an experiment going on. So we have to focus on that. And we will answer your questions when we have gaps. You cannot interrupt. So, yeah, I would actually exclude the range from 145 to 155 and fit to the rest.
So like here to here?
Yeah, even 143 to 155. I would ignore that in the fit and fit to everything else, because you basically want to fit to the wings of the galaxy. You not want to fit to, you want to define the wings of the galaxy. And I think reflecting the right side is the way to do it.
Okay, so
Raja, is it correct that you can, for example, I mean, if you want to slip out something, you first determine where the peak of the transient is, and then just take a symmetrical range around that, right?
Exactly. I would take it. So I was thinking this transient peak is at around 150, and I would remove plus minus 7 around that.
Right.
It's more important to remove the stuff on the left, because as a fraction, it is contaminating more of the galaxy's light, whereas when you go inwards, the galaxy is rapidly getting brighter, so the transient doesn't have as much of an effect.
Okay.
I mean, ideally what one does, ideally one doesn't actually clip anything out. You fit for two Gaussians. You fit a tall Gaussian and a narrow Gaussian, a tall Gaussian, a short Gaussian, with different centroids, obviously, different positions. You fit them simultaneously. That would be the way to do it. But I'm still saying that this is what you're seeing here is the continuum. It will not, the emission lines are far more complicated. It depends on what we're trying to do with the spectrum. What is our goal here? If the goal to measure the shape of the continuum, then yes, double, fitting for these two Gaussians simultaneously is the way to go. Is the goal to measure the continuum shape of the transient or the emission line of the transient? That's what is our science goal here? I guess this is a question for the whole science team.
I think, Roger, I mean, we are more interested in getting lines, but the lines are going to be used for classification. But one step that's involved there is we continuum normalize. And I think what's happening is because of that, the way it's been severely affected at the red side, the big dip we've seen, the continuum very it will be very wrong that I think will mess up short lines that we see.
So I'm going to suggest something quite heretical here. I think what we should do is take, you know how we're seeing this double Gaussian here. This is collapsing all of the wavelength information. You got this double Gaussian. Instead of collapsing all of the wavelength information, if you collapse it in, if you do a moving median, a long wavelength, that is, you take a range of wavelengths, you measure this double Gaussian, measure the relative intensities of the two peaks, and then you keep doing that. You keep shifting the wavelength range, repeat that. Shift the wavelength range, repeat that. Then you get the intensity of the galaxy and the transient as a function of wavelength. And you do this for the standard star. That allows you to flux calibrate these numbers from instrumental units to physical units.
Okay.
Yeah, I mean, ideally, I think that will give us the more or less like the best spectrum.
Give us the best spectrum, I think.
I believe, Stephanie, you want to do some sort of a quick classification, right? Like,
yeah.
So
I have to think. Yeah, sorry. Go ahead, Kimura. Go ahead.
So this is what I was thinking, Roger. Like, if you narrow down your literally, let's do this. This may not be, but so the right hand side is being affected, contaminated by the host, right? So
if we narrow down the aperture, if we narrow down the aperture, that might be a good way to do it. Yeah.
Okay.
The way to the left hand side, like literally, around the peak of the transient. So keep on shifting the to minus.
Move the right to the right and the left to the left.
Oh, okay.
Yeah, just look at the peak of the transient. No, move the right to the right. Move it in. Sorry, move the right to the left and the left to the right. Make the range narrower, not wider, right, Monika?
Yeah.
I misspoke. My bad. There. And the other side. Make it a really narrow thing. Even more, even narrower. Bring the right side in. Yeah, there we go. Now try this.
Okay. Should I shift my backgrounds more, or do you guys think this is kind of fine?
The background, you want to do a constant fit.
Yeah, exactly. Do a constant.
Order equals. Remove the right hand side. Like press a Z that would remove your, and then do. I'm maybe this one work, but order equals 0, or just type order 0. We'll see what it does. Okay, order 1, and then fit. Okay, yeah. This is just to let the algorithm not crash. So more or less, like we aren't subtracting anything. Like it's just at the base level. So